Alright, we're going to work our way through the second review packet, and I'm probably going to break this up into two videos, so we'll see how long this takes. If it goes much past 7 or 8 minutes, I think I'll break it into two. Alright, so let's look at the first problem. It says that a particular atom of iron contains 26 protons, 26 neutrons, 26 protons, 26 electrons, and 55 neutrons. What is the atomic number of this atom? Atomic number equals protons, so that is going to be 26. Then it says, what is the mass number? Well, mass number is protons plus neutrons, so if we take 26 and 55, that'll give us 81. So this problem is asking the difference between atomic number and mass number. The atomic number is the same as the number of protons, and that's going to give you the identity of the atom. In a neutral atom, not an ion, but a neutral atom, the number of protons equals the number of electrons. And we'll talk about ions in another review. How many sublevels are in the third energy level? Well, sublevels are going to mean orbital types. So in the third energy level, we have s orbitals, we have p orbitals, and we have d orbitals. So there are 3. And this one says, how many orbitals are there in the second energy level? Well, there's one s-type orbital, and there's 3 p's, so that's 1 s and 3 p's, so that's going to give us 4 total orbitals. And it says how many electrons can fit into the fourth energy level? Well, the fourth energy level has 1 s orbital, it has 3 p's, it has 5 d's, and it has 7 f's. And if you remember, one orbital can hold 2 electrons, so 2 can go in there, 6 there, 10 there, and 14 there, which is going to give you a total of 32 electrons in the fourth energy level. Alright, let's move on. Let me clear some space here. Alright, chlorine has 2 isotopes that occur in nature, and what we're going to be doing is calculating the mass of one of those isotopes. So the formula for average atomic mass is equal to the mass of an isotope times its percentage plus the mass of the isotope plus its percentage, etc. Now you have to memorize this formula for the final. That one is not on the formula sheet. So let's plug in our values here. It says one isotope accounts for 75.53, so remember, when we write percentages in math problems, we're going to move that decimal over 2 places. This one has a mass of 34.969. The other one accounts for 24.47%, and we do not know the mass of that one, but we do know that the average atomic mass is going to be equal to 35.458. So what we're going to do is the math here, and I'm going to save some time and just solve for x here, and you should get a value of 36.97. So I would multiply those two together, divide over here, and then do the division again. So again, if you want me to go through that math, just ask in class. Alright, let's move on. Let's clear that out of there. I wish that would do it automatically, but it doesn't. Alright, what is the energy of a photon of light with a wavelength equal to 650 nanometers? So energy is equal to h times nu. So what we need here is nu, which is frequency, given a wavelength. Here, let me try that again. So wavelength is equal to 650 nanometers. Now the conversion is 1 times 10 to the 9th nanometers for every meter, and if you do that math, you're going to get 6.5 times 10 to the negative 7th meters. Nanometers cancels, and we have meters. Remember, we need all distances for wavelength in meters. So then energy is going to be equal to H, which is a constant. That's on your equation sheet. Joules times seconds. Now we still need nu here, so we just have wavelength. So let's calculate nu. Nu is equal to c, which is a constant, speed of light, over our wavelength. And when we do that math, we should get 4.61 times 10 to the 14th inverse seconds. So that is our value for nu. So we are going to plug that value in right there. I don't have a lot of room, so just imagine that number here. And then when you do that calculation, you should get 3.05, sorry about the writing, times 10 to the negative 19th, and then the unit there is going to be joules. Okay, let's move on to the next one. Let's clear it out first and get a pen. Alright, this question is along the same lines. Again, we have a wavelength here equal to 510 nanometers. I'll just convert that right away. 1 times 10 to the 9th nanometers in a meter. Nanometers cancels, that's 5.10 times 10 to the negative 7th meters. Now we're trying to find frequency. So again, frequency is equal to c over wavelength, lambda. So again, c is a constant, 3 times 10 to the 8th meters per second, and our wavelength, which we just converted to the negative 7th meters. Do the math, and you should get 5.88 times 10 to the 14th, and that's frequency, so it'll be inverse seconds. And again, you just want to make sure that you know how to do scientific notation on your calculator. As we talked about throughout the year, that's a place people tend to make mistakes. All right, let's move on. All right, how many atoms are there in 15 grams of calcium chloride? All right, this is a classic dimensional analysis problem. So you know exactly what I'm going to say. What goes in the denominator? Grams calcium chloride. The only thing we can go to is moles. If we add up the molar mass, we have 40 for calcium, 35.5 for chlorine, so we should have 111 grams. This way grams cancels. We have moles of calcium chloride, but we need atoms. So let's do another conversion. Now we're going to go moles. Now we can't go moles to atoms because calcium chloride is not an atom, but we can go molecules. Now technically it's not a molecule either, but that's what we're going to call it. 1 mole. Look at your mole map and you have 6.02 times 10 to the 23rd. So now we'll have molecules there. So let's put molecules in the denominator. Now there's 3 atoms per molecule. There's 1 calcium and 2 chlorine, so we're going to say there's 3 atoms in 1 molecule of calcium chloride. So that way when they cancel and you do the math, you should get, what do you get? Actually, I did not do this in my calculator, so 1 second, we'll just do that real quick. We have 15 divided by 111 times 6.02 times 10 to the 23rd times 3, and that is going to give us, 2.44 times 10 to the 23rd atoms. And that is a lot of atoms. Alright, let's move on. We'll try to do this whole thing in one shot. Let's clear that. Get our pen back. Alright, we have another dimensional analysis problem. So we have 16 times 10 to the 23rd molecules, and again, that's not the proper way to write scientific notation, but we won't worry about that right now. And it's magnesium chloride, so we're going to go 6.02 times 10 to the 23rd molecules of magnesium chloride. The only thing we can go for molecules is moles. And again, my pen, there we go. Magnesium chloride. So molecules cancel. Now we want mass. So I'm going to continue down here. We can go from moles to grams of magnesium chloride. 1 mole, add up the molar mass, 24 plus 2 times 35. And that is going to give us 95 grams. So what's left is grams, and that's what we're looking for. Do the math there, and you should get 252 grams. All right, let's move on. We'll go to the next one. Let's clear our screen and get our pen back. All right. We have 25 grams carbon dioxide. Now we want to go to volume, which is liters. So we're going to put grams to moles, and this is carbon dioxide. 12 plus 32 is 44 grams. So our grams cancel. And then this is the simplest, I think, of all the conversions we do. 1 mole is 22.4 liters, and that's carbon dioxide. So moles cancel. Do the math there, and you will get 12.7 liters. And again, I'm going through these kind of quickly, but this is just a quick review for you to use. So if you have specific questions, ask again in class. All right, let's move on. Let me click to the next slide here. Whoops. Let's clear out and get a pen. Alright, now we're writing electron configuration. So sulfur is here. So if we wrote the whole electron configuration, we would start in the first row, 1. Remember, S1, S2, 2, S1, S2, 3, whoops, yeah, not 3 yet, 2P, 1, 2, 3, 4, 5, 6, 3s2, and then we go 3p, 1, 2, 3, 4. But remember, the noble gas configuration, what we're going to do is write the previous noble gas in brackets and then just tack on that last row, 3s2, 3p4. So for bromine, which is here, we would go through the whole electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2. Now remember, when we go into the D block, we drop back down to 3d, go through all 10 blocks, and then back to 4p, 1, 2, 3, 4, 5. So the noble gas configuration would be argon, 4s2, 3d10, 4p5. And remember, we're going to include that 3d10 even though sometimes you wouldn't. But for us, we will include that. All right, let's move on. We're going to do a little bit of practice with some naming and formula writing. So we're going to write the formula for the following compounds. So calcium chloride, IDE ending, metal, non-metal, so we have single elements, symbols, charges, crisscross, so Ca, Cl2. Next one, we have 2 non-metals and a prefix. There's no prefix in front of the first one, so we know it's 1. Di means 2. Sulfur dioxide. The Roman numeral here is the charge, so it's iron with a 2 plus charge. Bromide, IDE ending, crisscross, 2 goes there, 1 there. And hydroxide is that only polyatomic that we have with the IDE ending. Magnesium 2 plus. So now we're going to crisscross and put that 2 behind the hydroxide. So to do that, we're going to put that there. Do not forget your parentheses. That is very important for hydroxide. Let's move on. And again, I'm moving through these kind of quickly, so take some notes and ask questions in class. Now we'll name the following. We have more than 2 elements. We have a metal and a polyatomic, so sodium, that polyatomic is sulfate. Metal and a nonmetal, 2 elements, so potassium bromide, IDE ending. 2 nonmetals, first one is 1, so we don't say monocarbon, we just say carbon. And then we have tetra, 4, chloride. Copper and sulfate. Now copper is a transition metal, so we need to figure out what its charge is. That's the polyatomic sulfate. Now sulfate has a charge of 2 minus, so to maintain the 1-to-1 ratio, copper would have to be 2 plus there, so we are going to call it copper 2 sulfate. Alright, so again, we went through those pretty quickly, so this is just used as a quick review of how to do these problems. So again, if you have specific questions, just make sure you ask in class.